Hello students, in the last class we discussed about the order of the filter as well as cutoff frequency expression, where we derived the expression for order of the filter capital N as well as the cutoff frequency for the normalized Butterworth filter, that is omega c. So in the today's video we will solve some examples. Through these examples we are able to understand how to design the Butterworth analog low pass filter with a given the specifications. So here we have the problem statement. A Butterworth low pass filter has to meet the following specification. The passband gain Kp is equal to minus 1 dB. So the passband gain is given, Kp is equal to minus 1 dB, and passband edge frequency omega p is given 4 radian per second. Similarly, a stop band specifications are also given, that is the stop band attenuation is given, that is greater than or equal to 20 dB, right? So in order to calculate the order of the filter as well as cutoff frequency, what we need is we need passband gain as well as the stop band gain respectively. So here stop band attenuation is given. So the stop band gain is the negative of the stop band attenuation. So the stop band attenuation is 20 dB, means the stop band gain is given by minus of the stop band attenuation, that is Ks is known as stop band gain, which is minus 20 dB, and the stop band edge frequency is given, that is 8 radian per second. They are asked to determine the transfer function of analog low pass Butterworth filter HA of S, right, of the lowest order Butterworth filter to meet the above specification, right. So we have to design the lowest order Butterworth filter to meet the given specifications such as Kp, omega p, Ks as well as omega s, right. So now just we'll write down the given specifications once, then we'll solve by finding its order of the filter as well as cutoff frequency, right. So the passband gain is given, that is Kp is equal to how much it is, minus 1 dB. The gains are always defined in terms of dB, and similarly the attenuation is given, that is the stop band attenuation is denoted by As, right, which is minus of the stop band gain, and the stop band gain is Ks, understood. So here As is given, As is how much, it is 20 dB greater than or equal to 20 dB, therefore Ks is equal to minus As, that is equal to minus 20 dB per second. So please remember the gain is always negative of the attenuation, because if you see the magnitude frequency response of the Butterworth low pass filter, how is it looks like this, right. So this is, if you take the 20 log of this response, what you will get, here you will get 0 dB, right. So then, so this is your passband frequency omega p, and at this point the gain is Kp, right. Since it is below the 0 dB, means always you will get negative only, minus gain only, right. And if you take this one as the stop band frequency of omega s, and this is still lesser than, that is given by what, minus Ks, right. Ap and As are nothing but passband attenuation and stop band attenuation, they are negative of each other, right. So here Kp is given minus 1 dB and Ks is equal to minus 20 dB. Along with that, the passband edge frequency is given, how much it is, 4 radian per second. So omega p is equal to 4 radian per second, and omega s is also given how much it is, 8 radian per second. Understood? So to design the Butterworth analog low pass filter, right, which mainly depends upon what, the number of poles, and the number of poles are calculated if you know the order of the filter n, because the number of the poles k, which mainly depends upon 0, 1 up to what, 2 n minus 1, where n is the order of the filter, right? So our first job is always to find the order of the filter, and in the last video lecture we discussed what is the expression for order of the filter. So can you tell me what is the order of the filter here? N is equal to log of 10 raised to minus kp divided by 10. Kp divided by 10 means it is 1 divided by 10 means it is 0.1 kp minus 1 divided by 10 raised to minus 0.1 ks, because it is ks divided by 10, minus 0.1 times 10 minus 1 divided by 2 log of frequency. What is that? Pass band frequency omega p divided by omega s. Is that clear? So now let us use all these specifications. So log 10 raised to minus 0.1 into kp is minus 1, so minus into minus is plus 1, so it is 10 raised to 0.1 minus 1 divided by 10 raised to ks is how much? Ks is also minus 20, so this minus 20 into minus 0.1, you will get 2 here, minus 1 divided by 2 log of what is omega b, pass band edge frequency 4 radian per second, divided by what is omega s, that is stop band edge frequency 8, right? Let us simplify this one. Log of 10 raised to 0.1 minus 1, so simplify this, 10 raised to 0.1 minus 1, then 10 raised to 100 minus 1, right? And then take the log of that. So what you will get? You will get, after taking that, minus 2.58 you will get, divided by 2 log of 4 by 8. 4 by 8 is 0.5, log of 0.5 you calculate, multiplied by 2. So what you will get? So you will get minus 0.602. Simplify, you will get n is equal to 4.285, right? N is equal to 4.285, but we cannot say the order of the filter could be 4.285, it should be the integer value, right? The round value. So you have to approximately round up to what? Next integer value. So n is equal to how much? 5. So now the order of the filter is what? 5. And similarly you have to calculate the cutoff frequency. So this is the first step, and the second step is to what? To determine cutoff frequency. So what is the expression? Either you can use omega p divided by 10 raised to minus 0.1 kp minus 1 raised to 1 divided by 2n. We have two equations, either you can use first one or second one. Understood? So I will go with omega s divided by 10 raised to minus 0.1 ks minus 1 raised to 1 divided by 2n. Here what is the value of n? N is equal to 5. Understood? So omega s value I will substitute. Omega s is 8. Next 10 raised to minus 0.1 times ks, where ks is minus 20, so you will get 10 raised to 2 minus 1 into 1 divided by 10, right? And if you simplify this one, you will get 8 divided by so 100 minus 1 is 99 raised to 1 divided by 10. So you will get how much you will get? You will get 4.5787, right? So I am not discussing all the steps, right? So you just simplify and verify whether you will get the same answer or not. 4.5787 radian per second. So this is the cutoff frequency. Right? So next, once you find the order of the filter as well as cutoff frequency, next you have to do is you have to find the poles. Poles are very important to determine the transfer function. So how to find the poles? The poles are denoted by Sk in terms of its magnitude and base. So the magnitude is what? It is always 1 at an angle of theta k, where phase angle theta k is given by what? It is given by, yes, pi k divided by n plus pi by 2n plus, you just recall whatever we discussed in the previous video, you just recall, and finally it is pi divided by 2, yes, where k varies from 0, 1 up to 2n minus 1, right? So 2n minus 1 means 2 into 5 is 10, 10 minus 1 is 9, so up to we will get 0 to 9, right? So we will get how many number of phase angles here? 10 angles you will get, and all those angles, with respect to angles you can locate the poles over the unit circle in the z domain. So this is right half of the plane, right, and this part is left half of the plane. So you have to consider only the left half of the plane, not right half of the plane. So whatever the poles lies on the left half of the plane of this unit circle, you have to consider only those to find the transfer function, right? So now let us calculate. Here theta k is equal to pi k divided by n. N is pi plus pi divided by 2 times n means how much it is? 10 plus pi divided by 2. Is that clear? Now you substitute k is equal to 1. Theta 1 is equal to k is equal to 1. So it is pi divided by 5 plus pi divided by 10 plus pi divided by 2. Right? Right? So how much you will get? Theta 1. So theta 1 you will get 4 pi by 5. 4 pi divided by 5. Similarly, we forgotten to calculate theta 0 also. You calculate theta 0. So first term vanishes because k is equal to 0. So it is pi by 10 plus pi by 2. So how much you will get? 3 pi by 5 you will get, right? So similarly you calculate theta 2. So theta 2 you will get pi. Theta 3 you calculate. Theta 3 you get 6 pi by 5. Theta 4 you calculate. So you will get 7 pi by 5. So next theta 5, right? So instead of wasting the time in calculating all, so if there are 10 poles, out of those 10 poles, the first 5 poles S0, S1, S2, S3 and S4, so these 5 poles located on the left half of the plane, and next 5 poles will be locating on the right half of the plane. So what you do is, and to locate these, the location of these poles are mainly based on what? Their phase, right? That is the direction. So that is theta 0, theta 1, theta 2, theta 3, theta 4. So the location of these poles mainly depends upon these phase angles, right? So if you are interested in only these 5 poles, you calculate only these many number of phase angles, right? So don't waste your time in calculating the remaining the phase values like theta 5 to up to what? Theta 9, right? So that's why I will calculate only up to what? Theta 4, right? If you want, you can calculate the remaining also, but just to save the time I am telling you to calculate only theta 0 to what? Theta 4. So once you calculate this one, you will calculate S0. So S0 is equal to, magnitude is always 1 because it is a unit radius we have considered. And what is the angle? Theta 0. So it is 3 pi divided by 5. And convert this polar form into the rectangle form or Cartesian form. So what you will get? So you will get minus 0.309 plus j 0.959, right? Similarly, you calculate S1. So S1 you will get minus 0.809 plus 0.588, and similarly S2 you will get, S2 is equal to minus 1, S3 is equal to minus 0.303 minus 0.959 J, and this is conjugate symmetry of S0, right? And similarly S4 will be the conjugate symmetry of S1, right? So what is S1? Yes, S4 equal to minus, sorry, not conjugate, I am not sure. Let's calculate. That is S4 is equal to 1 with a phase angle of 7 pi by 5. If you calculate this one, minus 0.309 minus 0.95 G. This is theta 4, and theta 3 is 0.809 minus J 0.588 minus J 0.588, right? So these are this one and this one are conjugate symmetry, and this one and this one are conjugate symmetry. So once you find this one, next is what? You can find the transfer function. Yes. Once you find the force, next you can find its transfer function, that is 1 divided by, only considering left half of the planes. The force lies in the left half of the plane, right? So how many force lies in the left half of the plane? 5, right? That is S minus S0, S minus S1, S minus S2, S minus S3, and S minus S3, right? So already we have S0, S1, S2, S3 and S4. So this is S4. So this is S4. Substitute all S0 to S4 and simplify by multiplying each, then you will get HA of S is equal to this. So this is the HA of S, that is the transfer function, right? And then, but omega c is not equal to 1 radian per second, it is not normalized. So the calculated cutoff frequency omega c is not equal to 1 radian per second, because how much you got? We got 4.5787 something, right? That's why you have to transform the low pass to low pass. You have to apply the low pass to low pass transformation. How? You have to replace S by S divided by omega c, where omega c is equal to 4.5787, right? So here S is there, right? So S divided by 4.5787 square like this, and after simplifying, finally we will get HA of S. In the next video we will discuss one